Welcome back to the deep dive. You know, we spend a lot of time on this show talking about the flashy stuff, the generative AI, the neural networks with billions of parameters, the things writing poetry and painting pictures. It's easy to get dazzled by all that.
It is. It's the headline-grabbing technology for sure.
But today, I want to look under the hood at something else. Something you probably use, I don't know, maybe every single hour of every single day. And you probably never give it a second thought.
Right.
We are talking about the invisible workhorse of natural language processing.
It really is invisible.
Yeah.
I mean, we get so caught up in the AI revolution that we forget the foundational mathematics that actually makes things like text search, spell checking, and, speech recognition fast enough to work on your phone.
Exactly.
Without this stuff, your battery would be dead in an hour and your autocorrect would be, well, it just wouldn't exist.
So for this deep dive, we're digging into a fascinating piece of research. It's titled Finite-State Technology in Natural Language Processing by Mans Holden.
A fantastic source.
And our mission today is really to unpack how these abstract mathematical models, some of them dating all the way back to the 1940s,
Literally pre-Silicon Valley.
are still running the show when it comes to understanding and manipulating human language.
And what I love about this source is that it's a reminder that new isn't always better.
Right.
Sometimes the elegant, efficient solution from 70 years ago is still the best tool for the job.
So let's get into it. The core concept here is the finite state machine. Now, be honest with me. When I hear that, I picture a robot doing a very stiff dance.
Yeah, that's a common image.
But we're talking about a specific way computers process sequences, right?
Precisely. To really get it, we need to strip away all the complex code and just look at the basic engine, the finite-state automaton, or FSA.
Okay, let's try to visualize this for everyone listening. The source material uses a pretty standard notation, which is basically a diagram. So imagine a piece of paper. You draw a bunch of circles.
Right, and these circles are states. You can think of them as snapshots of where the machine is in a process.
And connecting these circles are arrows.
We call those transitions, and each arrow has a label on it, usually a letter from the alphabet.
So it's basically a board game.
That's a great way to think about it.
You start at the initial state, that's usually the circle numbered 0, and you have a word you want to check. You read the first letter, you follow the arrow with that letter to the next circle.
Read the next letter, move again.
And if you can follow the arrows all the way to the end of the word and land on a final state,
Which is usually marked with a double circle.
then the machine says, yes, I accept this word.
And if you get stuck, or if you finish the word but you're not on a double circle.
Then the machine says, rejected.
Exactly.
Yeah.
It classifies everything in the universe into two buckets, accepted or rejected.
It's a very binary way of looking at the world.
Very.
But here's where it gets really cool. The source gives a specific example that made this click for me. The cat and car example.
Ah, yes. Figure 10.1.
So imagine you want this machine to recognize a list of words. Cat, cat's car, cars, dog, dogs.
Right. Now, if you or I were to write that list on a piece of paper, we'd write C-A-T. Then on the next line, C-A-T-S. Then C-A-R.
We're rewriting the letters C and A over and over again. It's redundant.
Extremely redundant. But a finite-state automaton doesn't do that. You have start state. Then you have one single arrow labeled C going to the next state.
Yeah.
Then one single arrow labeled A.
I see. So the machine doesn't care if you're eventually going to spell cat or car or caterpillar.
Not at that stage, no.
It just knows you've started with cat.
Precisely. The path is shared. It only branches off when it absolutely has to.
Yeah.
At the T for cat or the R for car.
And this allows huge word lists to be stored in a very, very compact structure.
You're collapsing all the common prefixes and suffixes into a tight network.
So that's how my phone can hold a dictionary of hundreds of thousands of words without using up all its memory. It's not a list, it's a web.
It is a web, a highly optimized one.
But the text also mentions that these machines can handle an infinite number of words. How does a finite machine, that's right there in the name, finite state, handle infinite words?
Through loops, or, as the text calls them, cycles.
Cycles.
Imagine you have an arrow that points back to the state you just came from, or even an arrow that points back to itself. If you have a loop on the letter E, the machine could accept sheep, sheep, sheep.
With 100 E's, you can just spin around that loop forever.
Exactly. So if the graph has no loops, it's acyclic, and it handles a finite list of words.
But if it has loops, it's cyclic and describes an infinite language.
You got it.
That makes sense. Now, there's another major distinction in the source that we need to clarify because apparently it really affects how fast these things run.
Determinism versus non-determinism?
DFA versus NFA. It sounds like a wrestling match.
In a way, it is. It's a match between ease of design and speed of use.
Okay, break it down.
Let's start with the deterministic one, the DFA. This machine is, well, it's strict. At any given circle or state, there is only one outgoing arrow for a specific letter.
Okay, so if I'm at state 1 and I see the letter A, there's only one road I can take.
Correct. It is completely unambiguous. It's like a well-marked highway. You never have to guess.
Which implies that the other one, the non-deterministic one, is messier.
Messy is a good word for it, yeah.
Huh.
In a non-deterministic finite automaton, an NFA, you might be at a state and see two different arrows, both labeled A.
So the machine has to choose.
Or explore both paths.
Yeah.
And it gets even wilder. You can have what's called an empty transition or an epsilon transition.
An empty transition.
Where you can move to a new state without consuming any letters at all. It's like a teleporter.
Wait, so the machine is reading the word cat. It reads the C, and then poof, it just jumps to a new state without even reading the A yet.
Exactly that.
Why? Why would anyone want that? That just sounds like chaos.
Well, it's incredibly useful for design. Humans are just better at designing NFAs because we can draw lines wherever we think a connection logically exists.
You don't have to worry about the strict rules.
Exactly. But computers hate guessing. Guessing is slow. They prefer that strict highway of the DFA.
Right.
A DFA runs in what's called linear time, which means the time it takes to check a word only depends on the length of that word, not the size of the entire dictionary.
So we have a dilemma. Humans like designing the messy way, computers like running the strict way.
But there's a solution. The source mentions the subset construction algorithm.
Okay.
It's a mathematical method that can take any messy NFA and convert it into a perfect, strict DFA.
So we can design the easy way and then let an algorithm bake it into the fast way.
That's the workflow. Now, there is one catch that Holden points out.
Oh.
The conversion can sometimes make the machine exponentially larger. It's called state blowup.
That sounds dangerous.
It can be. But the text reassures us that in practical linguistic applications, this rarely happens. Language is structured enough that we usually get the best of both worlds.
Okay, so that's the engine. Circles and arrows saying yes or no. But language isn't just about spell checking. We need to actually change things, translate, conjugate.
That brings us to the next evolution in the chapter, the finite-state transducer, or FST.
The translator.
Right. Think of the automaton we just discussed as an acceptor. It just nods its head yes or no. The transducer is a machine that actually outputs a translation.
So how does the diagram change?
The arrows change. Instead of the labels having just one letter, they have pairs.
Pairs, like X, Y.
Correct. An input symbol and an output symbol. The text uses a classic example from morphology, the study of word structure.
The geese example.
Exactly. So the input isn't just the word geese. The input is the abstract analysis.
The meaning. We call that the upper language or the domain.
Right. So it's goose plus the tag noun plus the tag plural. Goose plus N plus PL.
And the machine follows the arrows. It reads GOSE, sees the plus N and plus PL tags, and the outputs, the lower language, spits out GESE.
It translates the abstract instructions into the surface word. But here is the real superpower of these FSTs. They're bidirectional.
Yeah, really, you can run the same machine backwards.
Yes. If you have the transducer built, you can feed geese into the bottom, the lower side, and it will output goose plus N plus PL at the top.
That is incredibly efficient.
One map for both generation and analysis.
But I noticed the text talks about sequential transducers being the gold standard, and this goes back to our discussion about determinism, doesn't it?
It does. A sequential transducer is just like the deterministic automaton. When you're reading the input, you never have to guess which path to take.
But English is messy. The text gives the example of mouse.
Yeah. The mouse example is a great one for this problem. If the input is mouse plus N plus PL, what is the output?
Well, usually mice.
Usually. But what if you're talking about computer mouses? Then it might be mouses.
So because there are two valid options, the machine can't be perfectly sequential. It has to hesitate.
Exactly. It breaks that strict one arrow only rule. The text does mention a compromise, though, called p-subsequential transducers.
Which just sounds very technical.
It just means we allow for a little bit of ambiguity, usually pushed to the very end of the word. It keeps things fast while handling the fact that language isn't always, perfectly logical.
Speaking of not being logical, real life is definitely not a binary yes-no. Sometimes we're not sure what a word is, the audio is fuzzy, or I mistyped something. It's more of a probably.
Right. How do we handle that uncertainty? This is where we get into weighted automata.
This was the part where the math started getting a little heavier, but I think the core idea is pretty clear. The transitions get a weight or a cost.
Think of it as a toll road. Each arrow you take costs you something. And the text uses a great example, the word about.
Figure 10.4. I loved this because it validates my lazy speaking habits. It shows 4 different ways to pronounce about. You have the proper way, about. But in casual speech, you might just say bout.
Right. Or drop the T at the end. The point is, bout is much more likely in a casual conversation than the full, Queen's English pronunciation. So the weighted automaton assigns probabilities to these paths.
So one path is the full pronunciation, one drops the A, one drops the T. And to get the total probability, you combine the weights along the path.
If you're using raw probabilities, yes, you multiply them. But here, the source introduces a concept called the semi-ring.
The semi-ring. It sounds like a secret society in a fantasy novel. The Order of the Semi-Ring.
It does. But really, it's just the rule book for how the math works inside the machine. Because, see, computers actually hate multiplying tiny probability numbers.
Why is that?
It's a problem called underflow. You multiply $0, times another 1, you get $0, Do that a dozen times, and you have a number so small the computer just rounds it down to 0.
So how do we fix it?
We change the semi-ring. We use the log semi-ring. Instead of multiplying probabilities, we take their negative logarithms and add them.
So it turns multiplication into addition. That's much easier for the computer.
Much easier and more stable. But the coolest one mentioned, and you have to admit, it has the best name, is the tropical semi-ring.
The tropical semi-ring. I'm picturing a mathematician in a Hawaiian shirt with a pina colada.
The text doesn't explain the name, but the function is what really matters. The tropical semi-ring encodes something called the Viterbi approximation.
Which is?
It's the winner-takes-all approach.
Mm-hmm.
In the tropical semi-ring, we don't care about the sum of all the possible paths. We only care about the best path, the one with the lowest cost.
Okay. So if I mumble about into my phone, the computer uses the tropical semi-ring to find the single most likely path that matches my mumble.
And it ignores all the wildly improbable ones.
It just assumes I probably meant the most likely thing.
Precisely. Which makes processing incredibly fast.
Okay, so we have the engine, the translator, and the weights. But surely engineers don't sit there drawing millions of circles and arrows by hand.
No, that would be impossible. That's why we use code, specifically regular expressions, regex.
I've seen regex. It looks like someone fell asleep on their keyboard.
It can look cryptic, yeah.
Yeah.
But there's a famous theorem called Kleen's theorem that proves that any regular expression can be converted into a finite-state automaton. They're mathematically equivalent.
So regex is the shortcut. The engineer writes the compact code, and the computer expands it into the circle and arrow machine.
Correct. But for NLP, standard regex isn't quite enough. We need replacement rules.
This is the A-B stuff. Replace A with B.
Yes, but more specifically, conditional replacement. A, B, all, R.
Replace A with B, but only when it is between left context L and right context R.
And this is crucial for mimicking how human language actually works. The text gives the improbable example, which I think illustrates this perfectly.
Right. Let's break that down. The word is probable. You add the prefix in for not, so logic says it should be improbable, INP.
Right. But try saying improbable 10 times fast.
Improbable. Improbable. It's clunky. My tongue hits the roof of my mouth for the N, then my lips have to close for the P.
Exactly. It's inefficient for your mouth.
Yeah.
So over centuries, language evolved. Your lips want to close for the P, so the N naturally shifts to an M, which is also a lip sound.
Improbable. Much smoother.
That is called nasal assimilation. And we can model that with a single rule. N becomes M whenever it appears before a labial consonant like P or B.
So the engineer writes that one rule, NMP, and the machine automatically handles that transformation for every single word.
Exactly. Improbable enters the machine. Improbable comes out. It handles the nuances of human speech without us having to manually program every word.
And this logic applies to things like tokenization too, right? The longest match concept.
The its example, the aft operator.
Right.
If the text says January 2011, and you have a machine looking for dates,
you don't want it to just grab Jan 1 and stop there.
January 1 is a valid date, but January 1, 2011 is a better, longer date. The longest match rule tells the machine, don't be lazy, look as far ahead as you can to find the most complete pattern.
So we have the engine The translator, the weights, and the rules. Now, how do we actually use this to build something like Siri? The source highlights one final superpower.
The secret sauce. Composition.
Composition.
This is what lets us chain these machines together. Suppose you have machine A that translates language X to language Y, and machine B that translates Y to Z.
Composition lets you smash them together into one machine C that goes straight from X to Z.
Exactly. And the key is that you do this offline. You bake them together before the user ever even touches it.
The text describes a cascade for morphological analysis. You have a lexicon transducer, that's the dictionary of roots, and then you have rule transducers for spelling changes like fly plus S becomes flies.
Instead of running the word through the lexicon, getting an output, then feeding that output to the rule machine.
You just compose them.
Lexicon composed with rules. You get one giant machine that handles the entire language structure in a single step.
That is mind-blowing efficiency. It explains why my phone doesn't lag when I'm typing. It's running one pre-calculated path.
And it gets even more powerful when you apply it to speech recognition. This is the noisy channel model.
Okay, lay this up for us. This part feels like sci-fi.
So imagine you're speaking to your phone. The audio is the noisy channel. It's distorted. It's a mess of sound waves.
The input is just noise.
We can model the solution with composition. You have your input. You compose that with a perturbation transducer. That's an error model.
It knows how sounds get confused, like F's and Z's sounding alike.
Right, and you compose that with a language model, which knows which words are likely to follow each other grammatically.
So the formula is input composed with error model composed with language model.
A sandwich of logic. And because they are weighted transducers, using that tropical summaring we talked about.
The computer just has to find the least cost path through that massive composed machine.
That is a very accurate way to put it. When you say recognize speech, the computer isn't thinking. It's finding the path of least resistance through a giant maze of sound-alikes and grammar rules.
That explains why sometimes it makes funny mistakes. The cheapest path wasn't the right one.
True. But considering the complexity, it's amazing how often it is right.
It really is. So let's recap. We went from simple circles and arrow states and transitions all the way to complex probability models that can transcribe human speech in real time.
And the takeaway from Holden's chapter is that while this notation was invented in the 50s, it hasn't gone away. The tropical summaring and transducer composition are the invisible engines of modern NLP.
The source even suggests that despite the hype around neural networks, these finite-state methods remain the workhorse.
They do, because they are efficient, and just as importantly, they are explainable.
You can see why it made a decision.
With a finite-state machine, you can trace the path. Neural networks are often black boxes. FSMs are transparent maps.
And in a world where we are increasingly relying on AI, having a map seems like a pretty good idea.
I would definitely agree.
So the next time you type a text message and your phone automatically changes te to the, just remember, there is a little invisible state machine in there, frantically following arrows, calculating weights on a tropical summaring, just to make you sound a little bit smarter.
A very helpful machine indeed.
That's all for this deep dive. Thanks for exploring the math behind the language with us.